So in this directory, we have 3 files. Reveal, that's the program that we wrote. That does the decryption. And what it takes is 2 inputs. When you get an update, in the case of Tipping Point, when you get an update, you get actually 2 files. You get the actual signature file, which is sig_2.2.0, blah, blah, blah. And then you get another file, in this case it's signer.pem, which is just your typical OpenSSL certificate. So the key within the sig file is combined with the key in the code to then use the certificate to decrypt the file. So that's what we're going to do. We're going to type in reveal. Signer.pem, foo.tar. And it's a tar format. So we tar xvf, foo.tar, and then we get the files in there. And one, of course, you'll notice in the middle there is signatures.xml. So we go to the directory, and there are the files. So let's grep ZDI, signature.xml. So then we have all the signatures. We can also vi signatures.xml. How many people here are familiar with Snort? How many people here are familiar with other IDSs and their internal architectures? Okay. So what we see here is what we would find for a lot of products. In this case, most products these days, in the old days, they didn't use XML. And of course, XML is like the one true religion, so all products now ship their stuff in XML. So here's like IP options, record route. Of course, that's a very simple signature. That's the first one in the file. It's a 10 megabyte file, and so there's lots more stuff down below. But we see what we would expect for signatures. It's got signature ID, it's got some tests here, it's got some description text, some links. A lot of these are very similar to Snort, but just broken out if you imagine Snort in an XML format. So we can then search for ZDI. Okay, this is a ZDI signature. So this is net backup, BB Java miss, format string vulnerability. So that's interesting information. And this is one that the ZDI got through their program. They worked with the vendor to solve the program and stuff and put protection in their product. So let me go down here, and then we get a lot of the data. So this one doesn't tell us much about the vulnerability. So we see typical format string stuff. So all this is telling us pretty much is it's looking for what we expect for a format string vulnerability, like 9090, which is like nopsled plus like %x%x%x. So, but that's the simple trigger. A lot of these things also have more complicated regex. So the way that Tipping Point works is it does a simple pattern match first very, very fast, and then more generic, powerful regex expression. So a lot of these signatures, though, have better stuff that give us more specific stuff about the vulnerability. Now, unfortunately for Dave and I, we don't have a subscription to Tipping Point service. So the only files that we have are the ones that we get either when we buy a box from eBay or when we talk to our customers that sometimes have the product that will give us a file to look at. So a lot of these, though, when we go down and look into them, we find that they have stuff, when we look at the regexes, that can help us more specifically build exploits from them. So that was the issue with the Macintosh. There was a contest earlier this year. It's kind of well known. You guys have probably all heard about it. In CanSec West, where they offered $10,000 to someone who can break into a Macintosh. And so the ZDI program offered the $10,000. It started out with a smaller thing of just saying, you'd win the notebook. That's what the CanSec West organizers started with. And then the ZDI piled in and said, hey, let's make it more interesting. Let's put our money where our mouth is. So they offered $10,000. And, of course, someone found the bug. They had broken into QuickTime for Java. And so then there was these rumors that the exploit had been sniffed. The rumors turned out to be false because the person who claimed them said he'd sniffed the wireless and got the exploit, but the test actually had no wireless connection, it was wired, so it probably was false. But anyway, so ZDI said, okay, since there's a risk that the exploit's out there, let's publish the zero-day rule. So we know of two different groups that then took the rule file from that, decrypted it, and then based exploits upon what they saw within the signature for the exploit. So even though the exploit hadn't leaked out the way that the person had claimed it did actually leak out through the ZDI process. So that's really the point of the talk, is that it's a two-edged sword. Is you're shipping out your protection, and then yet you're also helping people. You're also helping the hackers. It's a risk that you're protecting the hackers. I mean, you're notifying the hackers. This is another signature. And so that's what happens. So the signature actually contained these strings, QT pointer ref and get size. And when you Google that code, when you Google those strings from the signature, you get links, all sorts of Google links to real source code for doing normal stuff. And when you look at that, you say, well, as a hacker, I can do these tests, and I can probably see how I can disrupt it. The reason it worked was that Java was a front end from back-end QuickTime utilities. The back-end QuickTime stuff didn't have the robust buffer checking that Java does, but Java passing things on through overflowed the buffer. So one thing, we're kind of beating up on Tipping Point here because they have the very well-known controversial ZDI program. But what we showed here applies to every other product. Is every single product we've looked at on the market, every other IPS, it's fairly straightforward. So the process of I can find some strings, I can look at where the strings are in the code that tell me it's decrypting, I can find the decryption function, and I can trace through it and replicate it in my own code. So that applies to every other vendor. Tipping Points responded fairly well to this. When we notified them, they immediately pulled back the 0-day from their updates. So all the updates all the 0-day that was a danger of being disclosed, they immediately pulled that back. And then they restructured the program to have stronger NDAs with people so that the typical customer doesn't actually have the 0-day stuff, but the ones that they got NDAs that they can trust. For example, the customers won't give us those files ourselves, so we can't decrypt them. That's who they give the 0-day stuff to. So that was actually very quick in response. They've also, we haven't had a chance to, of course, verify this, but they've made some changes so our techniques no longer work. Of course, our techniques still work from older equipment. So if you've got all these older files, our tool will decrypt them. The changes they made also were slight changes. And here's the big issue, is that to really protect this stuff, you need to be really designing the system from the ground up for protection. You need to make it hard for us to pull out the hard drive from the system and get the image. So when you look at your cell phone, when I try to break into cell phones like this, the cell phone has a lot of protection that I simply can't pull out the flash chip and change it and stuff and tweak it and read from it because they don't want me reverse engineering the cell phone. So that's the sort of stuff you need to add. Another thing we need to add is pre-compiling the signatures. So PCRE contains functions that say take a regular expression and then convert it into a binary blob that the engine actually uses to evaluate the regular expression. So if a vendor, instead of shipping those regex, were to ship the compiled PCRE, it would make our life a lot tougher. We can see the signature file, but now we always see these maybe base64 encoded blobs, and they don't mean anything to us. We have to then take that signature and then reverse engineer it back to what the original regular expression was. So PCRE's compiler tools only go one way. They compile the regular expression, but it's hard to extract it. Now, of course, then we might write a tool that would take any PCRE regular expression and compile back to the normal regex. But if they make some minor changes to the PCRE code, it would totally defeat that tool. So that's what companies need to think of. If they've got dangerous content within their security products, they need to think through, I need to defend them the same way that maybe DRM companies defend their DRM. Another suggestion is the way that viruses protect themselves. A lot of viruses these days do not want the antivirus companies reverse engineering how the virus works. works. So what the virus writers do is they put lots of code around the virus to protect it. It mutates itself. It checks to see if it's running under a debugger. It has specific code sequence that confuses the IDA Pro disassembler, because they know what their opponents are doing. So you should put those techniques in the code as well. So in this case, it took us about 5 days to do the reverse engineering from beginning to end. 5 days worth of work, plus 2 days of just going off for coffee while IDA Pro sat there and turned away. So with adding these techniques, it could take us 6 months to try to figure that out, or even a year. We'd still be able to do it. This is not like a vulnerability you can fix, but yet you can make our life a lot tougher. And then us lazy hackers can't just spend 5 days and get a nice 0-day stream. We'd have to do a lot more work, and we are much less likely to do that. Any questions on this part of the presentation? Question? The VxWorks image. Tipping Point, like a lot of routers and other IPS products, runs on VxWorks. And just like your mobile phone, by the way, it's one big image. So it's not like a file system with lots of little programs. It's one huge image. So that's what we disassembled. Other questions? Cool. So that was mostly Dave's work, actually. This part was mostly my work. So this next part is another lazy attacker's guide to attacking stuff. We all know that we can sniff stuff off the local Wi-Fi network. So BlackHat has a public Wi-Fi network. And we all know that we can just open our laptop, sniff it, and we can discover all sorts of wonderful stuff. But what we're lacking is tools that put that together and make it easy for us. So what we developed was a tool that is specifically targeted at Web 2.0. Most of the applications out there, like MyBook, MySpace, Facebook, Gmail, Yahoo Mail, Hotmail, they all work with a common architecture. They use SSL or some other encryption to encrypt the password when you log on, so that a person sniffing the wire cannot gain the password. But they generate a unique session key, and then that session key is what's used from that point on for the session. So all I have to do is sniff the wire, find that session key, and then I can then hijack other people's connections. There's two ways you can do that. A lot of these Web 2.0 applications put the session key in the URL. So you'll see a URL like something.com, blah, 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 ID equals this long number. Other companies use them in the cookies. URLs are pretty easy to hijack because I can just copy the URL from a sniffer and just type it into my browser, and then I've hijacked the connection. Cookies are a little bit harder. So let's look at cookies. The way cookies work is they contain the state of the information. HTTP is kind of an odd protocol that it's stateless. I make individual requests that are self-contained. So there's no memory between one request to the next request, what's going on in the system. So this was fixed by Netscape with cookies. What happens is the server sends the browser some information, say, hey, when you give me your next request, please add this little bit of information onto it. So for example, I don't know who your username is from one browser click to the next. I'll send up the username as a cookie. So, hey, Mr. Browser, next time you click on a web page, please send me, as a cookie, the username. That's one sample. Cookies have a number of attributes.